Greetings, Physics 112 students. Hope you're having a wonderful day today. I'm making this video to help you out with your some homework, your unit, let's see, 2-1, number 6 here. And it says a point charge of 39 microcoulombs. Now mine says 39, but it's in red. I wrote it in red here. That means you're going to have a different value. It's sitting in this field, this 295 Newton per Coulomb field. One thing I'd like to point out, if you folks will humor me, the picture actually looks something like this. They drew this electric field vector in their picture so that it's the same length as this distance for some reason. One thing I'd like to point out is the length of the electric field vector has exactly nothing to do with that distance, and there's no reason to draw this vector this length at all. So I'm going to go ahead and deliberately make it a different length here, and maybe I'll send them an email about that. But, you know, the length of this vector represents the 295 newtons per coulomb that I have right here. And the length of the distance represents whatever this distance is, and they're just entirely different quantities. Doesn't even make sense to compare them. But all right, let's start thinking about what this thing says. So it says find the electric force exerted on the charge. So, all right, forces. Remember how the electric field is defined. The field magnitude, let's say, is force per unit charge, okay? So there's one of these given in the problem. There's one of these given in the problem. That should be pretty easy to find the force on it. The force is going to be to the right on this object because the field is to the right and the electric field is defined around the force direction on a positive charge. Right, part B, it says the work done by that force. So quite simply, you know, part B, work is force times distance. You've calculated the distance, and this also is sitting in the problem somewhere, so you're going to get a number. Now, some things you got to keep in mind are plus and minus signs. You'll have to decide if that work term is positive or negative. Keep in mind that the object, here it is, and the force is to the right, and I believe it's moving to the right. So you can go back and review my videos on plus and minus signs on work if that's not familiar to you. The change in potential energy of the charge. So that's a conceptual question. I'm going to let you think about that. Ooh, hold on. Ooh, sorry about that. This is how I always kind of remember these as well. Think about a gravity problem. Here's a mass here. Position 1. It accelerates down to position 2. The work done by gravity is the force, which is mg, times the distance h, and this is some positive number. Your PE1 would be mgh, assuming datum at the floor. Your PE2 is 0, again, datum at the floor. So your change in potential energy is minus mgh, because we went from mgh to 0. And you can kind of see the relationship here between the work done and the change in potential energy. Effectively, it's the same thing with this question. Part D, where it says the difference in potential between A and B. So when you're calculating potential difference, I'm going to put potential difference magnitude-wise as field strength times distance. Then I could leave the minus sign off. Given in the problem, given in the problem. Now you just have to decide, I like people to have to do it this way. Is it a drop in potential or an increase in potential? And ask yourself which point is at the higher potential, red or green. So that should be enough to get that one done. I hope you enjoy the video. Have a great day.